So welcome to today's lesson. We're going to be looking at centripetal acceleration and force. We're going to be looking at circular motion, but this time from the perspective of forces and acceleration. So what we'll be doing first is identifying what is this force that's actually making an object move in circular motion. Then we're going to use Newton's law, second law specifically, F equals ma, to describe then the acceleration from that force. And then we will actually define some equations so that you can do some calculations based on linear speed and angular velocity. First though, let's warm up some concepts from last week. The radius of a clock is 10 centimeters. What is the linear speed then of the tip of the second hand? So here is our second hand. It moves around once a minute, right? So it takes 60 seconds to go around. What is the speed at the tip? And then from there, what is the angular velocity? Hopefully you've calculated a value of linear speed of 0.010 meters per second, remembering to use the right units, and then the angular velocity 0.10 radians per second. Good. That should get you nice and warmed up. So let's talk about an object moving in circular motion. When an object is moving, there are two perspectives. The first one is to consider the velocity vector, the way that it's actually moving. What direction is the velocity vector going in? Now, when an object is moving round, what we're actually doing is in each instantaneous moment, the motion is at a tangent to the circle, right? So at this particular moment in time, this satellite, which is moving in a circular path, has actually got a directional vector which is at a tangent to the circle surface there. So the velocity vector is always at a tangent. And then the centripetal force, by definition, very important definition, acts perpendicular to the direction of the velocity vector. So it always acts towards the center of the circle. Okay. Now, a great illustration of how we know this is to show what happens when this force stops. What happens to the motion of the object when this force is no longer to the center? So if you tie something up with a piece of string, like you get a little weight or an object, and you tie a piece of string, you start swinging it round, you can well imagine that if the string suddenly breaks, the path of that object stops being circular and in fact becomes a projectile, usually in the direction of something fragile. But that projectile has an initial angular velocity, which is always perpendicular to the motion, right? To the force, sorry. So the force used to be in this direction, and so the velocity vector is at a tangent, 90 degrees, and so it will go off like a projectile, like this. The following video gives you an illustration of this.
This is a great demonstration for showing that if something's moving in a circle and you remove the centripetal force, it'll move in a straight line. But if you're teaching circular motion, I've got another demonstration that's worth doing first. This is a really simple way to introduce some basic ideas about circular motion. The ball moves in a horizontal plane, which makes it easier to understand the forces involved than with, say, something moving in a vertical circle, because we can ignore gravity. When I do this with my students, I place an object about there, and I ask them to tell me when I should lift the hoop so the ball knocks it down. Right, so as a physics teacher, I knew when to lift the hoop because I knew the ball would go off at a tangent. But that's not obvious to everyone, and this demonstration can really help to clear up misconceptions about things flying off radially when you remove the centripetal force. The ball goes from moving in a circle to moving in a straight line, and we know from Newton's first law that if something is moving in a straight line at a steady speed, the resultant force on it is zero. So what's going on when it's in the hoop? Well, the hoop exerts a contact force on the ball at right angles to its surface, and that force changes the velocity of the ball. The force is always directed towards the centre of the hoop, the centre of the circle. Take away that force and the ball obeys Newton's first law and carries on moving in a straight line. This is true of all objects moving at a steady speed in a circle. The instantaneous velocity is always at a tangent to the circle, and the force keeping it moving in a circle is at 90 degrees to this, that is, towards the centre of the circle. We describe the resultant force that makes something move in a circle as a centripetal force, and it's important to emphasise to students that this word simply tells us the direction of the force and nothing more. The force may come from a contact force, as in this example, or friction, or gravity, or tension in a string, or any combination of these forces, so it's really important to look carefully at any particular situation to identify the origin of the centripetal force. This is really just a more exciting version of the demonstration with the hoop and the ball, and it's not as dangerous as it looks. If you're going to do this in class, wear some goggles and a lab coat to protect your clothes from any stray sparks. Stand your students a couple of metres back in a plane that's parallel to the plane of rotation of the sparkler. You simply jam the sparkler into your drill, making sure it's secured tightly, bend it at 90 degrees, ignite it, and off you go.